Digital twins, the innovation backbone of the future, delivering virtual representations of real-world products, systems, and cities. For example, the digital twin of an electric motor not only showcases form, but also analyzes functions. From the rotation of the shaft, to thermal conductivity, to data from sensors, and beyond. What's more, the digital twin continuously evolves thanks to the flow of data, user experience feedback, and new input. And it's greatly impacting development, production, and operation. In development, a product's behavior can be simulated and tested long before a physical prototype has been built. For example, Siemens utilized the digital twin to develop a world record-setting electric aircraft motor that not only weighs 50 kilograms, but is also 5 times more powerful than comparable electric motors. But it doesn't stop there. Digital twins also unleash the power of 3D printing. In a recent Siemens study for gas mixing systems, insights from the simulation of form and flow behavior were combined with generative algorithms. The result? A truly unique channel shape and configuration, one significantly more efficient than anything previously designed. Even entire factories down to individual machines can be simulated and tested. For instance, robots. It's difficult for them to perform milling tasks because large forces in the manufacturing process lead to inaccurate movements. But with the digital twin, the forces that push the robot away from the milling path can be calculated and compensated in real time, keeping the robot in its path. When it comes to operations, digital twins can compare the sensor data of a real point in real time with the simulation of its point. The availability of the point parallel to operations can be reliably predicted and sudden disruptions become a thing of the past. But this is just the beginning. Merging digital twins with artificial intelligence allows computers to independently design advanced products. For development, production, and operation, the digital twin breaks with traditional paradigms and opens up extraordinary possibilities. That's why digital twins are the innovation backbone of the future. Quite a few work around digital twins happening around the industry, in many industry software, in aerospace and defense, for instance, and automotive companies, complex multi-domain systems are very increasingly software-defined and autonomous nowadays. In transportation, energy, and industrial companies, new functions are being added to legacy systems that are increasingly data-centric for operations and maintenance. In software, internet, and financial services companies, big data and agile development and integration with IT systems are driving innovation. For medical and health companies, collaboration between science and engineering, along with informatics, are making a huge difference. And in electronics and semiconductor companies, a wide range of processors are enabling hardware and software interaction. And finally, in communications industry, the disruptors like 5G are paving the way for innovations across various industries. And technology-leading companies derive business value from innovations in engineering and science. And this experience allows us to share insights, best practices, and trends with business across many industries. For example, reducing carbon emissions is driving innovation in various industries. And it's a key focus of the energy industries as well. So companies are challenged to conform to regulatory and competitive pressures, while achieving both top-line and bottom-line growth. And it's a challenge that the oil and gas industry recognizes as well. So that's a high-level challenge. But what about the challenges at an operational level or at a plant level or at an engineering level? And here are some common challenges that you may have faced or you're involved in solving. And although you might be monitoring the operation, that doesn't mean it's the same as figuring out how to optimize the operation. And it may be easy to add sensors across the plant, but it's not easily associated to process KPIs such as say quality or yield. And sometimes, samples being tested in a lab in parallel to process on the way. It adds a lag to understanding the impact before the overall process. And in initial, there's complicated physical behaviors and first principles models which are used to understand the process. But these are sometimes too complicated to understand the overall system dependencies and nonlinearities. And that's where digital twins come in. With digital twins, the promise is you can make your operational system smart and connected. And with operational data, you can inform the operations to do things better. And these are all possible and things that are being done today. And the applications, some of the applications and benefits that you hear of digital twins are things like these. It grants you visibility into operations, allows you to perform things like predictive maintenance, and simulate various scenarios, do what-if studies, and obviously optimize your operations. And here is an example of one such production process or a planned process. So it's common to have traces of plant output layer sensors and actually have traces at sensor locations throughout the plant. But the leveraging that information to understand the overall process can be a bit challenging. And so this is where statistical approaches like principal component analysis or more recent AI-based techniques have come in. And they allow you to better understand the plant, better understand the concept and the context, and analyze system-level KPIs. And these approaches are well suited to address things like drift in the process and identify, say, good batches versus bad batches. And at the same time, you also have unit-level operations that can be modeled with first principles and the laws of physics. So these can be modeled with concepts like energy or mass balance, and often are modeled with process simulators for many cases. And I know this can begin to be combined to model the overall system process. And the more powerful is being able to combine both these techniques to get virtual representations of the complete process and how it impacts the KPIs. So let's talk about how these models can be used for the overall benefit, and that will come in the later part of the presentation. But how do you go about building these digital twins? For instance, for system operators, they have control on how the system resources are used, and they're able to see operational data coming off of the system. And this data is the first thing that can be used to model what is deemed useful. If appropriate, then physical domains and conservation laws can be applied. And this can be augmented to create other digital twin models. And in general, these can be combined to create hybrid digital twins of the process. And how a system is a mixture of components, that's how models are also created. A mixture of physics-based techniques and data-driven techniques. And overall, domain knowledge is useful to make sure that the right models are created and brought together. And then once it is modeled, it needs to be eventually deployed or acted upon. And the ultimate goal is things like operations optimization, or predictive maintenance, and fault detection and diagnostics. And technology industry use these digital twins, and these span multiple applications.